Hello, my name is Shivani and this is my lab 2 report. So the overview of this lab is essentially to estimate the amount of charge on each piece of tape necessary to float one tape above the other using a line charge model. This is in contrast to the point charge model that we applied in lab 1. So we're also specifically going to model the charge as distributed evenly along length rather than as a point charge, and then compare the estimates from the point charge and the line charge. So some of our key concepts, of course, are Coulomb's law, as we have down here at the bottom highlighted. We also want to highlight the fact that this is a uniformly distributed charge. So we want to think about charges on slices and these infinitesimally small particles that we are going to add up the contributions for each of these little pieces to get the change in E. Our core assumptions here are that all the U-tapes have approximately the same charge. We're going to ignore air resistance, and we're going to assume that this charge is evenly distributed along the length of the tape, and then some ideal conditions like no significant charge loss when we actually end up charging and using the different tapes. So the experiment itself, as sort of highlighted here, involves clear tape, desk, a ruler, and meter sticks. We essentially charged these two U-tapes and suspended them above each other, measuring some distance and some key data. We're using this data from lab 1. And so this is a little bit of what we did last time. Kind of like if you look on the right, that's the most important. The density of the tape, the length of the tape is 0.21 meters, and the distance between the tape is 0.0105 meters. So from our code results, we basically got the charge on each tape is about 5.26 times 10 to the power negative 9. Here's the line charge value, the net electric force, gravitational force, charge magnitude that's consistent. And so we also want to highlight that the current charge leads to a net upward force. And right here is sort of the code that demonstrates all this information, indicating that there are further real world factors at play. So some of our assumptions again are equal charges and charge distribution on both tapes. Some of our sources are error include air resistance, variability in tape preparation, and repeated use of the same tape in trials. So here are some of our additional questions, and this is where we're kind of getting to what this lab is mainly about, right? So the model showed that the distributed line charge provided a more accurate representation of the forces involved, comparing to treating the tape as a point charge. So the line charge model provides a more accurate estimate because it reflects sort of the real world distribution of a charge. In actuality, like when it's treated like a point, the electric field strength is overestimated near the center and underestimated at the edges, and that leads to some pretty important discrepancies. So here is our conclusion that the magnitude of the line charge is 5.26 e to the negative 9. The line charge model provided a more accurate representation of the electric forces between the tapes. Thank you.